If the universe began in a moment none of us could witness, no cameras, no eyewitnesses, no rewind, then how do we know anything about it at all? How do you prove a beginning you can't watch, using only what's here, now, in your hands and in the sky? Tonight, you and I are walking into the scene long after the event. The explosion is over. The smoke is gone. But the evidence, quiet, everywhere, unavoidable, still lingers. It's late. The lab lights are dimmed to a soft, tired glow, the kind that makes the corners of the room feel farther away than they are. You can hear the ventilation breathing. You can hear your own pulse if you stop and let the silence thicken. And then, if you've ever tuned an old radio between stations, you know that sound. The hiss. The stubborn, textureless that seems like nothing. It's easy to treat it as junk. As electronics. As the universe not cooperating. But what if that hiss is the opposite of junk? What if it's the oldest message you will ever receive? Because the universe is not silent. It has a background signature. It has a kind of fossil light, still washing through the cosmos in every direction, still arriving here like late mail from an ancient sender. We're not staring at the Big Bang itself. There's no window where you can simply look at time zero. We're reading the oldest surviving testimony. A record written in light, stretched thin by the expansion of everything. So treat this like an investigation. Not a lecture. Not a museum tour. A case. You and I are forensic scientists of reality. The crime scene tape is the horizon of the observable universe. The witnesses are dead. The event has cooled. But the evidence remains, embedded in a glow that fills the sky, even in the dark between stars. Here's the question that will guide us: what is the universe still whispering, and how did we learn to translate it? To answer that, we have to travel, but not with a spaceship. We travel by decoding. The moment you understand what the cosmic microwave background is, you start to feel time differently. Not as a straight line behind you, but as layers, like sediment, where the deep past can still be touched if you know which layer you're brushing against. Picture the early universe not as empty space with a few things inside it, but as a whole reality packed with energy, hot, dense, bright, and violent in the quietest way. Bright, because light was everywhere. Violent, because everything was colliding with everything. There's a word for this stage that can sound sterile: plasma. Here's the human translation. Imagine a foggy night drive. Your headlights are on full beam, but the fog is so thick that light doesn't travel far. It scatters. It bounces. It comes right back at you. The world is glowing, but you can't see through it. That's the early universe. A glowing fog. Photons, particles of light, are trying to fly straight, but they keep smacking into free electrons. The universe is so hot that atoms can't hold together. Electrons are loose, like sparks in a storm. Every time a photon tries to escape, it gets redirected, like a pinball in an infinite arcade. So even though there is light everywhere, there is no clear view. The universe is bright, and yet opaque. Then, something astonishing happens, not with fireworks, but with cooling. Expansion is not just the universe getting bigger, it's the universe losing temperature as it stretches. And about 380,000 years after the beginning, already older than any civilization we've ever built, but still newborn on cosmic timescales, the temperature drops enough for a revolution of tenderness. Electrons finally settle down and bond with protons to form neutral hydrogen. In the language of physics, this is recombination. That word makes it sound like paperwork. Here's what it really is: the moment the fog clears. Once electrons are locked into atoms, photons stop bouncing constantly. Light finally travels freely, not inches, not meters, but across the universe. That first free-streaming light is released like a curtain being pulled back. And that curtain, stretched and redshifted for nearly 14 billion years, still exists as a faint glow we can detect today. We call it the cosmic microwave background, the CMB. It is, quite literally, a photograph of the universe when it was only 380,000 years old, except the film is the sky itself, and the camera is any instrument sensitive enough to detect microwaves? And now comes the first mind bender. That light was once blindingly hot, thousands of degrees. But the universe has expanded so much that the light's wavelength has been stretched like taffy. Hot visible or infrared light becomes cold microwaves. Today, the CMB is at about 2.7 Kelvin, just 2.7 degrees above absolute zero. Let that settle. You are sitting in a world bathed in ancient light cooled to the temperature of deep space. You are not in darkness. You are in a sea, just one your eyes can't see. So if the CMB is everywhere, why wasn't it discovered the moment we invented telescopes? Because it's quiet. Because it hides in the microwave part of the spectrum. Because the universe whispers in frequencies we didn't evolve to sense. But we built theirs anyway. And here's where the case file starts to thicken. The first clue isn't the CMB itself, it's its perfection. In the 1960s, when engineers and astronomers started detecting a persistent microwave noise, it sounded like, well, that radio hiss. It didn't care where you pointed your antenna. It didn't go away at night. It didn't vanish in a different season. It was stubbornly, eerily uniform. Uniform radiation could mean many things: instrument error, local interference, a messy galaxy problem. But there's a test that turns confusion into clarity: measure the spectrum. A perfect thermal glow, what physicists call a blackbody spectrum, is like a fingerprint of equilibrium, of a system that once was dense and hot enough for matter and radiation to share temperature. If the universe truly began in a hot, dense state, the leftover light should look like an almost perfect blackbody. COBE, NASA's Cosmic Background Explorer, measured it. And it wasn't just close. It was astonishing. A near-perfect blackbody curve, as if the universe had once been a single, well-mixed furnace. That's when the CMB stopped being a speculation and became evidence you could put on a table. A cosmic artifact with a label. From the early universe. But a perfect glow creates a new problem. If it's too perfect, it's useless. A perfectly smooth universe would remain smooth forever. No clumps. No galaxies. No stars. No planets. No you, no me. So the next question becomes intimate and urgent. Where did structure come from? That's where anisotropies enter the story. A long word. Here's the metaphor. Anisotropies are the wrinkles in the cosmic sheet. The CMB is almost the same temperature everywhere, but not exactly. There are tiny variations, on the order of tens of microkelvin. Differences so small you could hide them in the rounding error of your thermostat. And yet those tiny differences are everything. They encode the earliest density variations, slightly heavier regions and slightly lighter ones in the primordial matter-energy soup. Gravity is patient, and it has no mercy for imbalance. If one region is denser by a fraction of a fraction, it pulls more strongly. It grows. It deepens. Over cosmic time, those tiny imprints become the scaffolding of galaxies, the filaments of galaxy clusters, the spiral arms of star systems, the chemistry of planets. If you want the human-scale version, those faint temperature freckles are the reason your brain exists to wonder about them. Now, when you first hear temperature map of the sky, it sounds abstract. But I want you to feel the scene. Imagine you're inside mission control of the mind. The monitors show the entire sky as an oval projection. Colors represent differences you can't feel, but you can translate. Redder means slightly hotter, bluer means slightly cooler. At first, the map is a blur, like a security camera from the 1980s. You can tell something is there, but you can't read it. Then comes WMAP, the Wilkinson Microwave Anisotropy Probe. The picture sharpens. The blotches of temperature variation become coherent patterns. And then Planck, the European Space Agency mission, refines it further, like switching from standard definition to a forensic grade scan where the smallest details matter. Every improvement is not just prettier. It's a tighter interrogation of reality. Because those patterns aren't random decoration. They are a code. So what does the code say? The first thing it says is, the universe is old, but not infinitely old. It has a measurable age. The second thing it says is, the universe is made mostly of things we can't see directly, dark matter, dark energy, with ordinary atoms as a minority. The third thing it says is, space is close to flat on large scales, like a vast plane that doesn't curve back on itself the way a sphere does. But I'm getting ahead of the story. Because before we trust any of these conclusions, we have to confront a paradox so unsettling that it feels like the universe is mocking our assumptions. Look at the CMB in two opposite directions of the sky. The temperature is almost exactly the same. That's beautiful. It's also impossible, at least, impossible in the simplest picture. Why? Because of causality. Causality is the rule that says influence travels at a finite speed. In our universe, that speed limit is the speed of light. No signal, no push, no, hey, match my temperature, can travel faster. Now rewind to the moment the CMB was released. At 380,000 years, the universe is much smaller than today, but still enormous. The regions that will later become opposite sides of our sky are so far apart that, even at light speed, they shouldn't have had time to communicate, to exchange heat, to agree on a shared temperature. And yet they did. This is the horizon problem. In plain language, how did the universe coordinate itself without a way to coordinate? Stand with me in that confusion for a second. Because this is the moment every serious investigator recognizes. The current theory explains a lot, but something doesn't quite add up. And that doesn't add up is not a failure, it's an invitation. So scientists proposed an idea that sounds almost like myth when you first hear it: inflation. Inflation says that, extremely early, far earlier than the CMB, in a fraction of a second, the universe underwent a burst of expansion so rapid that a tiny, causally connected region was stretched to cosmic scales. Here's the metaphor. Imagine you're looking at a small patch of dough that has been kneaded until it's smooth and uniform. That patch has had time to settle into the same texture. Now imagine you roll it out violently fast into a pizza the size of a city. Every part of the pizza can still be uniform because it came from one tiny patch that actually did have time to equilibrate. Inflation is the universe doing something like that, taking a small, connected region and stretching it so large that, later, we mistake its far-apart parts as if they were always strangers. They weren't. They share a common origin. But inflation doesn't just solve the temperature agreement. It does something even more poetic and unnerving. It turns quantum uncertainty into the blueprint of galaxies. Quantum fluctuations are the tiny, unavoidable jitters of fields at microscopic scales. You can think of them like the restless tremble in a perfectly still pond, except the pond is the fabric of reality itself. In normal life, those jitters average out. They stay microscopic. But if inflation stretches space dramatically, it stretches those jitters too, taking tiny variations and blowing them up into macroscopic differences in density. So the seeds of cosmic structure may be the magnified echoes of quantum randomness. If that's true, then when you look at the CMB anisotropies, you're not just seeing early universe weather. You're seeing quantum mechanics written across the sky. And that's where the investigation becomes almost unbearably intimate. Because quantum physics, so often confined in our minds to labs and particles, may have shaped the distribution of matter that eventually formed your home galaxy, your star, your planet, and the calcium in your bones. Now, how do we test inflation? Not by vibes. Not by poetry. By fingerprints. The CMB contains more than a pretty map. It has statistical structure. When you take that sky pattern and you analyze it, breaking it down into angular scales, you get something called the power spectrum. If that term makes your eyes want to slide away, hold on. Here's the metaphor. The power spectrum is like taking a song and asking, how much bass? How much treble? Which notes are loud, which are quiet? You're not listening to the melody directly. You're analyzing its ingredients. In the early universe, before the fog cleared, matter and radiation formed a tightly coupled fluid. And fluids can ring. If you compress a region, pressure pushes back. Gravity pulls inward. Pressure pushes outward. Gravity pulls inward. That tug-of-war creates acoustic oscillations, sound waves, but not in air. Sound waves in a plasma of photons and baryons, the normal matter made of protons and neutrons. Let that image land. The early universe was not silent. It was ringing, like a drum head the size of the cosmos. Those waves created regions of compression and rarefaction. Some areas got slightly hotter, some slightly cooler. And when recombination happened, when the fog cleared, the universe took a snapshot mid-vibration. The ringing froze into the CMB pattern. In the power spectrum, those frozen waves show up as peaks and dips. Each peak is a clue. The position and height of those peaks tell us the recipe of the universe. How much normal matter, how much dark matter, how much curvature, how the expansion behaves. This is where the investigation feels like a miracle of method. Because you're telling me, we're telling ourselves, that from one ancient light field, we can infer the age of the universe, its geometry, and its composition. Does that sound like overreach? It would, if the physics didn't lock together so tightly. But even as the standard picture becomes impressively consistent, the universe leaves a few smudges on the evidence bag. There are anomalies. A cold spot, an unusually large region of slightly lower temperature. Hemispherical asymmetry, one side of the sky seems statistically different from the other. A low quadrupole, less power on the largest scales than the simplest models expect. Now, any honest scientist has to do something emotionally difficult here: resist the seduction of significance. Because randomness can generate patterns that look meaningful. In any big dataset, you can find a weird patch. So we ask, are these flukes? Or are they cracks in the wall that let us peek at deeper physics? Maybe something about what happened before inflation, or whether inflation happened at all, or whether our observable universe is just one region of a larger structure? And then there's a more elusive suspect, one that would change the case completely if we caught it: primordial gravitational waves. Gravitational waves are ripples in spacetime itself. Not ripples in a medium, ripples of the medium. Like the surface of the ocean, except the ocean is geometry. Inflation, in many versions, should have produced a background of gravitational waves. Those waves wouldn't show up as temperature spots the same way. They would leave a subtle twist in the polarization of the CMB, an imprint called B-mode polarization. Polarization is the direction light's electric field points as it travels. If temperature is the brightness map, polarization is the orientation map. B-modes are like faint spirals, curl patterns in that orientation. A whisper inside a whisper. If we detected primordial B-modes cleanly, it would be like finding the original soundtrack of inflation encoded in the sky. But the universe does not hand over its secrets without trying to confuse us. Dust in our own galaxy can mimic B-modes. Instruments can introduce artifacts. Analysis choices can bias results. So the investigation becomes almost philosophical. How do you avoid convicting the wrong suspect when the evidence is faint and the noise is persuasive? This is where science becomes less like a list of facts and more like a discipline of humility. We build better detectors. We map foregrounds. We cross-check teams. We repeat. We publish uncertainty, not just results. We accept that "I don't know yet" is not a failure, it's the correct shape of the truth at the boundary. Now I want to stress test our whole reality model with a thought experiment. Imagine you're an alien investigator. You arrive in a dead quiet solar system. No internet, no libraries, no fossils, no DNA samples. Just physics. You look up and you detect the CMB. You map its temperature anisotropies. You measure its polarization. You compute the power spectrum. Could you reconstruct our cosmic history from that alone? At first it feels absurd. Like trying to reconstruct the entire life of a person from a single fingerprint found on glass. But that's exactly the point. A fingerprint is small, but it's structured. It's the compressed output of an entire developmental process. The CMB is like that. It's one field, one sky, one ancient page, yet it encodes an origin story because the laws of physics preserve correlations. So yes, in principle, you could infer the universe's age. You could infer that it expanded from a hotter, denser state. You could infer the existence of dark matter by how the peaks line up. You could infer geometry by how angular scales project. You could infer how much normal matter exists by the relative heights of acoustic peaks. And then, if you were truly patient, you could infer something even stranger, that the universe's large-scale structure grew from tiny initial perturbations, amplified by gravity over billions of years. This is the moment, if you let yourself feel it, where the entire investigation snaps into focus. We don't know the beginning because we saw it. We know the beginning because the universe kept receipts. It kept records in the way light cooled, in the way density fluctuated, in the way waves froze when atoms formed, in the way geometry shapes what angles we see. Physics is not just how things move. Physics is how the past survives into the present. And that realization changes the emotional texture of existence. Because you start to see yourself not as a creature trapped in the now, but as a reader of traces. We live by traces all the time. Memory is a trace, your brain carrying patterns of past experience into the present. Scars are traces, tissue remembering an injury. Fossils are traces, stone remembering life. Archived data, old photos, the wear pattern on a staircase, the smell in a childhood room you haven't entered in years, traces. The CMB is the cosmos doing the same thing. Carrying its past forward, not as a story told in words, but as a field of radiation that still fills every cubic centimeter of space. And now the most personal bridge of all, you are not outside this narrative. The atoms in your body are downstream of those tiny anisotropies. If the early universe had been perfectly smooth, gravity would have had nothing to amplify. No stars would have formed. No heavy elements would have been forged in stellar cores. No carbon. No oxygen. No iron in your blood. You are, in a literal physical sense, a late-time consequence of slight unevenness in an ancient light field. So when you look at the CMB map, you're not just looking at a distant object. You're looking at a family resemblance. A pattern grown out of an older pattern of light. And if you're watching this in January, at the start of a news cycle on our calendars, let's strip away the sentimentality and keep the awe. This isn't about holidays. This is about scale. Every year of human history is a footnote compared to that first clear sentence written across the sky. The earliest readable page of the universe is still open. Still legible. Still arriving. Right now, this second, CMB photons are passing through you. Some of them have been traveling since before Earth existed, before the Sun ignited, before the Milky Way finished taking shape. They are landing, gently, on detectors on mountaintops and satellites in orbit, and they are also landing, quietly, on the planet itself, as if the universe refuses to stop telling the story. So what is the universe still whispering? It's whispering that the cosmos had a childhood. That it cooled and cleared. That it rang like a bell. That tiny quantum jitters may have become galaxies. That reality is stitched with cause and effect, and yet still leaves room for mysteries at the edges. It's whispering that knowledge is possible without time travel. Because the universe is lawful enough to preserve evidence. Synthesis, then, what we've actually learned on this journey, the cosmic microwave background is the oldest light we can see, released when the early universe became transparent. Its near-perfect blackbody spectrum confirms a hot, dense origin. Its tiny anisotropies are the seeds of all structure. Its acoustic peaks let us infer the universe's composition, geometry, and age. And its polarization may hold clues, still contested, still hunted, about what happened in the first fraction of a second. Now let me leave you with a thought experiment you can carry into your next ordinary moment. Washing a cup, walking to work, lying awake at night. Imagine the sky as an archive that never closes. Imagine that every direction you look is not just out there, but back then. If the past can survive as a field of light for 13.8 billion years, what traces are you carrying right now? Inside your body, inside your habits, inside your relationships, that will outlive the moments that formed them? And the next great question, The one that opens the next door. If the universe can preserve its earliest readable page so perfectly, what else is it preserving that we don't yet know how to read? If you want to keep going, click the video on the end screen, because the next investigation builds directly on this one, and it'll change the way you look at what you think is empty space. And if you want a reason to subscribe, I make these audits to separate what we know, what we think we know, and what we're still guessing, so you can feel wonder without surrendering rigor. One question for you, simple, but I genuinely want your answer. When you hear that the oldest light in the universe is still arriving here, right now, does it make you feel small, connected, or both?